What's up guys, and welcome to the first video in my series on integration, where we learn to solve integrals by doing exercises step by step. In this first video, we'll be focusing on how to solve integrals using the method of substitution. And I will be solving these 6 exercises step by step. And as always, these exercises will start out very basic, just to showcase how the method works. But they will get progressively more difficult towards the end, so feel free to skip around according to your own level. The timestamps can be found in the comment section below. And with that out of the way, let's get into the first exercise. The first exercise that we'll be looking at is the integral of 1 plus x dx. And you might immediately object that you don't need the method of substitution to solve this integral. You can simply write this integral of a sum as a sum of 2 integrals, the integral of 1 dx plus the integral of x dx, and you would get the answer in that way. And of course you would be completely right. However, it will not always be the case that you can rewrite the integral in that way. And it's a perfect example to showcase how our method of substitution works. The first step is to try and think of a basic integral of which we know the solution that our integral is most similar to. In this case, we know the integral of x dx, which is simply equal to 1/2 times x squared plus a constant. So we would like to rewrite our initial integral as an integral of x dx. And what is most similar here is that this x and here dx are equal. So we want to have the same in our initial integral here. So the substitution that we propose is that 1 plus x, so the function inside this integral, is simply equal to u. And filling this in, we find that we can rewrite our integral as u dx. And this is now even more similar to the integral of which we know the solution of. However, we have here that we have an x dx, and here we have a u dx. So what we now have to do is to rewrite this dx as a function of du. And to do this, we rewrite our substitution to get x is equal to u minus 1. And to get this result, I just rewrote our substitution. Then we differentiate both sides of the equality sign. So we have dx is equal to d of u minus 1. And this is simply equal to d of u minus d of 1. And we know that the differential of a constant, or the derivative of a constant, will always be 0. So we get that dx is actually equal to du, and we can just swap them out in our integral. However, note that this is not always the case, and we will always have to do this calculation to rewrite dx as a function of du. We can now fill this in our integral, so change dx with du. So we get u du. And of course we know the integral of u du. This is simply 1/2 times u squared plus this constant. And now we did the integration, but we still need to rewrite this again as a function of x. However, we know that u is equal to 1 plus x. So our result will be 1/2 times, we replace u with 1 plus x, and we square this, and we should not forget this constant c. And we already have our result that the integral of 1 plus x dx is equal to 1/2 times 1 plus x squared plus a constant c. What is always a good practice is to check our result to see whether we made any mistakes. And for integration, this check is very straightforward, because we know that integration is the inverse operation of a derivative. This means that if we derive our solution to x, then we should get again our initial function that we had to integrate. And if you're unsure about how to derive these functions, I gladly refer you to my other videos specifically on deriving functions. Doing this very quickly, we see that we get 1/2 times 2 times 1 plus x, because this squared gets pulled in front of the brackets, and the derivative of a constant is 0, so this one drops out. We can cancel this 2 and this 2, and we see that the derivative of our solution is indeed 1 plus x. And this is exactly the function that we had in our integral. So we didn't make any mistakes. And like I said at the beginning of this exercise, you could have easily gotten this result by simply splitting up the sum inside the integral and to get the sum of two integrals. However, this is not always as easy as it was in this exercise. For example, in the next exercise, we look at the integral of x minus 3 to the power of 4. Now again, you could rewrite this x minus 3 to the power of 4 as a sum of powers of x, and then take the integral of each of these terms in this sum. However, this would now become quite cumbersome, which is why the method of substitution is probably the best choice in this case. Again, we try to think of an integral, a basic integral of which we know the result that looks most similar to the integral that we have to solve. In this case, we know what the integral is of x to the power of 4 dx. Again, this is very simply 1 over 5 x to the power of 5 plus a constant. So again, we want to have something to the power of 4 d of something. So our proposal for substitution here is that u is equal to x minus 3, because in this case we will get the integral of u to the power of 4 dx. And as in the previous exercise, we now need to rewrite this dx as a function of du, because only then we will get u to the power of 4 du. To do this, we again rewrite our substitution. So we get that u plus 3 is equal to x, which is just rewriting this equation here. Taking the differential of both sides, we get d of u plus 3 is dx. And using the fact that d of a constant, d3, is 0, we can rewrite this as du is equal to dx. And we again see that we can simply swap dx for du. But again, this will not always be the case, as we will see later on. So we rewrite our integral and we get u to the power of 4 du, which is simply, as we've seen, 1 over 5 u to the power of 5 plus a constant. And rewriting this again as a function of x, using that u is equal to x minus 3, we get our result of 1 over 5 times x minus 3 to the power of 5 plus c. And this is our result for our initial integral. And again, we can very easily check that we didn't make any mistakes by differentiating our solution. So 1 over 5 times x minus 3 to the power of 5 plus c to x, to find indeed that we get x minus 3 to the power of 4, because deriving this constant gives us 0, and this 5 drops in front, which cancels with this 5, and the 5 becomes a 4. So indeed, we didn't make any mistakes. But again, we could have gotten this solution by expanding this fourth power of these brackets and then just calculate all of the integrals for each term in the sum. However, for the next exercise, we will see that this will not be possible, which is the integral of the square root of 2x plus 1 dx. And here we can immediately see that we cannot rewrite the square root in any way or form such that we get a simple integral. So this means that here we need to use the method of substitution to solve this integral. So the first step is to think of an integral that we know of which we know the solution. And of course, since we see the square root here, we know that the integral of the square root of x dx is simply equal to the integral of x to the power of 1/2 dx, which is just rewriting the square root as a power. And we know that this is simply 2 over 3 times x to the power 3 over 2 plus c. So we know the integral of the square root of x dx. We want to rewrite our initial integral in this form. So our proposal for substitution would be that 2x plus 1, the function inside of the square root, is simply equal to u, because in this case we get the integral of the square root of u dx. And again, as the second step, we need to rewrite this dx as a function of du. And to do this, we rewrite our substitution formula such that we get x is equal to u minus 1 divided by 2. And then differentiating both sides of the equation, we get dx is equal to d of u minus 1 divided by 2, which is equal to d of u over 2 minus d of 1 over 2, splitting this minus sign here. And we know that this is equal to 1/2 du minus 0, because the differential of a constant is 0. So we can just drop this. And in this exercise, we see that we cannot simply swap du and dx, because we need to take into account this factor 1/2 in front of it. Filling this in our integral, we get that our integral is equal to the integral of the square root of u times dx, and we know that dx is 1/2 du, so we get 1/2 du. Any constant can always be brought outside of the integral, so now we get the integral of the square root of u du. And we can simply solve this because we know what this integral is. So we rewrite this 1/2 and we write the solution of this simple integral, which we already had here. So we get 2 over 3 times u to the power 3 over 2 plus the constant c. So we get the final solution 1 over 3 u to the power of 3 over 2 plus c. And then rewriting our u as a function of x again, we get 1 over 3 times 2x plus 1 to the power of 3 over 2 plus c. And this is our final result for the integral of the square root of 2x plus 1. And again here, for good practice, we can check whether we made any mistakes or not. And in this case, we have to take the derivative of 1 over 3 times 2x plus 1 to the power of 3/2 plus c. And to derive this, we have to use a chain rule. We already note that deriving this constant will give 0, so this simply drops out. And we write 1 over 3 times 3 over 2 times the brackets 2x plus 1, which have their power reduced by 1. So we derive these brackets here. So the power goes in front and gets reduced by 1. And now we have to multiply by the thing inside of the brackets, which is a good example for the chain rule. And if this is not entirely clear to you, I refer you to my video where I explicitly make exercises on the chain rule in derivation. So we multiply this by the derivative of 2x plus 1 and we get 2. Simplifying this, we see that this 3 and this 3 cancels, this 2 and this 2 cancels, and we are left indeed with the square root of 2x plus 1, which is exactly the thing that was inside of the integral, so the thing that we had to integrate. So we know that we didn't make any mistakes. This concludes the basic exercises. So let's now look at a more difficult exercise. So we have to integrate e to the power of x divided by 1 plus e to the power of x dx. And as you can see, this is not as straightforward as the previous exercises, so we have to do some thinking. Again, the first step of using the substitution method is to think of an integral of which we know the result and is quite similar to the integral that we have to solve. In this case, the first integral that springs to mind is e to the power of x dx, which we know is simply, again, e to the power of x plus c. And this comes from the fact that deriving e to the power of x to x is simply, again, e to the power of x. So we propose a substitution where u is equal to e to the power of x. And in this case, we get the integral of u divided by 1 plus u times dx. And the second step is now to rewrite this dx as a function of du. To do this, we look at our initial substitution and we take the differential on both sides of the equation. So we see that du is equal to d of e to the power of x. And we know that the differential of e to the power of x is simply e to the power of x again, dx. Rearranging this equation, we get that dx is equal to du divided by e to the power of x. And here again, we see that we cannot simply replace dx with du, as was the case for the first two exercises. And we can even rewrite this further to be du divided by u, since we know that u is equal to e to the power of x. So we just rewritten this e power as u. Filling this in our integral, we get that the integral of u divided by 1 plus u times dx, but we know that dx is du divided by u, so 1 over u du. And we see that we can cancel this u and this u to get the integral of 1 over 1 plus u du. And at first sight, this integral doesn't really bring us closer to the result, because I have no idea what the integral of 1 over 1 plus u du would be. However, again, we can use the method of substitution a second time, because what we do know is that the integral of 1 over x dx is equal to the ln of x plus c. So this is an integral that we know. But here we have 1 over 1 plus u du and not 1 over u du. So we can again propose a substitution that 1 plus u, the thing in our denominator, is equal to a new variable, let's call it w. And this means that we can rewrite our integral as 1 over w du. And again, the second step is to rewrite this du as a function of dw. And this we can do by rewriting our substitution formula. And we get that u is equal to w minus 1, or that du is equal to dw minus d of 1. But this one becomes 0 because the differential of a constant is 0. So this one can be dropped. And we see that for the second substitution, we indeed can replace du by dw. So we have the integral of 1 over w dw, of which we now know the answer to be the ln of w plus the constant. Now, of course, our solution is now still written as a function of w, but our initial exercise was an integral as a function of x. So we want to rewrite our solution as a function of x, tracing back our substitution steps along the way. First, we know that w is equal to 1 plus u, so we get that the ln of w is equal to the ln of 1 plus u plus this constant. Then we know that u is equal to e to the power of x, so we rewrite this as the ln of e to the power of x plus 1 plus our constant. And this is our final solution, which is as a function of x, and is a solution to the integral of e to the power of x divided by 1 plus e to the power of x dx. And as always, we perform our simple derivation check to see whether we didn't make any mistakes. So we derive to x our solution, which is the ln of e to the power of x plus 1 plus this constant c. We immediately drop this c because the derivative of a constant is 0. And we use again the chain rule. So first we derive the ln of something, which is 1 over this something. And then we derive this something to x, which becomes e to the power of x. And this is of course e to the power of x divided by 1 plus e to the power of x, which is exactly the thing that we had to integrate. So we didn't make any mistakes and we are very happy. Let's now go to the next advanced exercise, where we have to solve the integral of x times cosine of x squared dx. And this is actually already a very complicated looking integral. However, if we just stick to the steps that we have to go through, we will eventually get to the answer. The first step is to think of an integral that we already know the solution of, so one of the basic integrals. We know here that we have a cosine of x, so let's just say that we think of the integral cosine of x dx, of which we know has a solution of sine of x plus c. How do we now try to rewrite our initial integral as an integral of cosine of x? Well, we see that we have here a cosine of x squared. A first step might be to propose the substitution that x squared is equal to u, because in this case, we get the integral of x times cosine of u dx. We first rewrite this dx as a function of du. We again do this by taking our initial substitution equality and take the differential on both sides of the equation. So we get that d of x squared is equal to du, and we can rewrite this as 2x dx, because the differential of x squared is 2 times x dx is equal to du. And rewriting this even further, we get that dx is equal to 1 over 2x du. And this is how we write dx as a function of du. So we rewrite our integral, and we get that the integral of x of the cosine of u times dx, but we now know that dx is 1 over 2x times du. And we see that we actually made the right substitution choice, because this x here cancels out with this x here. And what we are left with is simply 1/2, because a constant can be brought outside of the integral, times the integral of cosine of u du. And we know what the integral of cosine of u du is. This is simply 1/2 times the sine of u plus c. And again, we are not done yet, because we can rewrite this as a function of x. So this will be 1/2 times the sine of x squared, because u is equal to x squared. That is what our substitution was initially. And we cannot forget this c. And this is our solution to the integral of x times cosine of x squared. And as always, we can perform this very quick check by deriving our solution with respect to x and see whether we get our initial exercise back. So we derive the sine of x squared plus c to x. Again, this c drops out, and we get 1/2 times the derivative of the sine of something is simply the cosine of something, and in this case this something is x squared. And now we have to use a chain rule to still derive this x squared, so we get times 2x. This 2 and this 2 cancels out, so we get x times the cosine of x squared as a result. And we see indeed that this result as the derivative of our solution is indeed our initial function that we had to integrate in the first place. So we didn't make any mistakes again. Let's now go to the final exercise, which is the derivative of the cosine of x times the sine of x dx. And again, this does not look straightforward at all. So we think of an integral that we know of which we know the solution. Let's say, for example, we see a cosine and we say, well, we know the integral of the cosine of x dx, which is simply equal to sine of x plus c. However, at this point, we cannot really rewrite our initial integral as the integral of simply cosine of x dx, because we still have this sine of x here that, well, is simply not going anywhere. Plus, what would even be our substitution? Because we already have a cosine of x dx here, so we are not really sure on what the substitution will be. So this will give us a pretty much dead end. So we have to think of another integral that we know we can solve. So let's just try the integral of x dx, because we know that this will be 1/2 x squared plus c. And what we do now is to try to think of how we can rewrite this integral as something x dx, meaning that this x and the thing after the d is the same. Okay, so let's propose that cosine of x is equal to u. And in this case, we get that our integral becomes u times the sine of x dx. So now we still want to rewrite this dx as a function of du. To do this, we take our initial substitution equation and we differentiate both sides. So we get d of cosine of x is equal to du. Or written differently, we get the sine of x dx is equal to du. And rewriting this, we get that dx is equal to du divided by the sine of x. And now we already see that we probably made the right choice here, because if we fill this in our integral, we get the integral of u times sine of x, which is what we had here, times dx, but we know that dx is now simply du divided by the sine of x. And we see that this annoying sine of x here is simply dropping out because we rewrote this dx as a function of du. And what we are left with is simply the very easy integral u du, which we know is 1/2 times u squared plus c. And rewriting this again as a function of x, we use our substitution that we used in this exercise, and we get 1/2 times cosine squared of x plus c. And this is actually the solution of our exercise, which can be simply seen if we check our result, because we have to derive to x our solution, 1/2 times the cosine squared of x plus c. We again note that this c is simply 0, and we use the chain rule, so we get 1/2 times 2 times cosine of x, because if we derive the cosine squared of x, the square gets in front of it, and the power of the cosine gets reduced by 1, and only 1 power remains. But now we still have to derive the cosine of x using the chain rule, and we get sine of x. Cancelling these two and these two, we are simply left with the cosine of x times the sine of x, and this was exactly what we started with here, so we didn't make any mistakes. And this brings us to the end of this video. If you have any questions, please leave a comment in the comment section below. If you have any suggestions for future topics, also let me know in the comment section. If you liked the video, give it a thumbs up. And if you want to get notified by future releases, consider subscribing. And with that, I thank you for watching, and I will see you guys in the next one. Bye.